No, we can use them to stop me when I'm going too fast. Wait, we have a question?
I like R.
So somebody press them when I'm going too fast. Is it a buzzer there?
Wait, what does this mean?
Yes, please.
Once he starts.
Where is the yellow one? Did you guys see the yellow buzzer?
I need a buzzer.
Where's the yellow buzzer? Okay. Blue, red, green. Is the yellow anywhere?
We gave them the red.
Where's the thing?
I had no idea that this is a thing. Oh, you're little like.
Can you go next door to the Garcia's room and see if we left the yellow buzzer there yesterday? Oh, there it is.
Oh, thank God.
Give it to her.
What is it? I want Lego.
Why? Oh, you want it? I want like.
All right. Miss,
So can I press this one?
Mrs. Nauman? What's the first law? Shh. Okay, law of inertia, yes. Go ahead, give her legal. She said it's an object at rest will continue at rest. An object that's moving will continue moving. There's something missing from the end of that, right? As long as no force act on that. Go ahead and give her a legal, right? So this is. I would like to be able to to make it simpler than that, though, if possible, because basically saying an object at rest will stay at rest. An object moving will stay at moving unless a force would act on it. We could just say one thing to fix all that. Basically, an object's velocity cannot change unless a force acts on it. Now, what is change in velocity? Acceleration. So another way of saying that would be an object cannot accelerate unless a force acts on it. Is that clear? Any of those are okay. You can say what she said. You can say the object's velocity cannot change. But the way Newton actually said it was an object's momentum cannot change unless a force acts on it. All right? We'll learn more about momentum in a few chapters ahead. But the way that Newton actually described that is basically an object momentum is, for Newton, is the quantity of motion of an object. Inertia is the quantity of opposing motion. Are you with me? Which we'll talk about what that is in a second. But the quantity of motion is momentum. The way Newton phrased the law, and if you smart, you're writing the GLQ answers as we go along, and you have to have that on your little notebook, right? Which I'm going to check for you in the corner for all the GLQs we've done so far, right? Probably next class I'll start checking them because I have a Mastery Day next class, so I'll have downtime. I'll start checking on them. And also check your notebooks too, so make sure you have both of them with you next class. All right? So, the one I like is that one. An object's momentum cannot change unless a force acts on it. All right? Basically, the object cannot accelerate unless energy is applied to it. And that's what force is, applied energy to the mass. Okay? That's the first law. It's the law of inertia. I think of the law of inertia as the law that talks about the way that things stay the same. Are you with me? The universe has a tendency to stay the way it is unless something is done to it. All right? Not exactly accurate because of entropy and because of the dark energy and all that stuff. So it's not exactly accurate, but dark energy is accelerating the universe without any seemingly explanation so far in the realm of physics. But that's one of the things we need to work on as a scientist. Second law, law of Taro. What you got for second law? Hold on, I want law of Taro's answer, not the answer that's on her paper. What you were doing when we were doing the GLQs for the last 15, 20 minutes. That's the first question, so how did you not get to it? No, I want to understand, why are we in this place that you're no answer for this? What were you doing for the last 20 minutes? The next time that happens, like seriously, because I want to be mean, right? I want to make it as easy as marine biology is, kind of thing, right? Oops, that's on video now. All right, I don't want to be mean, but the next time that happens, all right, I'll collect all the GLQs on the spot, and then it becomes a quiz grade for everybody. All right? Because we shouldn't be doing that. Speaking of which, I started before doing the quiz. Let's stop and do the quiz. All right? So, please, clear desk, number 2, blank sheets of paper. Let's do a quick quiz on dynamics. And you can thank Lautaro for reminding me of that one. Yes. Also, from now on, if you miss the quiz, you're going to have to do something harder than the quiz to make up for it. If there's a day that you're not here, and we had a quiz, the way the mastery points work, the quiz is worth game points. If you didn't get those game points, you're just going to have to get them some other way. That's how it works. Alright? It's not that much anyway, it's 40 points. So you're going to have to do some sort of activity to make up for it. And I'll let you guys know what that is later. Alright. This is dynamics quiz. It'll be easy. It'll be easy. Only blank sheets of paper on the desk, nothing else. Close the notebooks for now. Tablets upside down if you have them in the desk. You just grab your stuff, put it on the floor really quick. And remember, the first thing with topic, you should already automatically set up those 2 blank sheets of paper on the side. Because then, as you're doing the GLQs, have that ready already. So then when I call out for the quiz, we can do that quickly instead of wasting time. Now we're going to have to invade the second day of dynamics to do this. I don't think we're going to have enough time, because this is also I wasted a lot of time at the beginning. But anyways, question number 1. This is weird. It's not is it telecasting? Because it feels frozen to me. Yeah, it's frozen on 15 minutes ago. The camera's frozen. Delete that. And then add a source. Let me just plug and unplug the camera. Shh. Can you go to add source and pick up that web camera, please? It will respond. Let's just leave it alone for a little while. It's not going to work. We'll leave you proactive then. I'm sorry, Teresa. I'm going to have to do this too. Okay, number 3. All right. This could also be called the object's quantity of inertia, or how much inertia the object has. It's another way of saying how much inertia something has. So this is also considered the object's quantity of inertia, or a measurement of how much the object resists accelerating. Think about that. Think about the second law and what it states, right? When you apply a force to an object, you get a certain acceleration, but it depends on the object's quantity of inertia. So what is the quantity of inertia that an object has? Okay. Number 3. 4. Which scientist came up with this law? You need a first and second.
Gets it wrong.
Full name. Full name. Yes. You need a full name. And you cannot miss the title. He had a title. He was a knight. Right? He was. He was a knight. He was knighted by the queen. Oh my God! Why did you say that? Why? I have to cancel all the questions. Yes, you said the answer wrong.
I didn't hear
Yeah, this whole.
How can we? I didn't.
That's okay. You can keep the question. That was a key anyways, wasn't it? Alright. Is that number 5 now that we're about to do?
Yeah. Can we take this now?
What are the units of force? The units of force. What are the units of force? And then we're going to have a 6th and last question. I want those same units, okay, of force in standard SI units, all right? Because the actual unit you probably wrote down is not a standard SI unit. You can only use kilograms, second, meters, Kelvin.
So is that number 6?
Yes, number 6 is get that unit. And you can use dimensionality if you don't know it, right? But you need to leave it in meters, second, kilograms, Kelvin. You know, there's standard SI units. If you don't know what that means, you can't really get it right then, right? What number 5 was a unit of force, right? But you cannot use that for number 6. I want you to actually put it in terms of kilograms, meters, and seconds, right? Yes. Number 3 was the quantity of inertia of an object. What is that called? Or how much the object resists changing its thing. All right, that was it. Make sure your name and class number is on it. Name and class number. Make sure your name and class number is on it. Then we're going to do this. We're going to pass the paper. We're a part of a big circle. We'll pass the paper 3 times this way. Next time, you guys are sitting there doing the quiz. The 2 of you, because I know you like sitting there. I have no problem. Doing the quiz, folks sit on the outside. If I have to remind you again, you get no grade for the quiz. Don't sit there doing the quiz. You guys are part of a big circle, so you guys will pass your papers to them, all right? It is a 19. Make sure your class number and name is on it. Pass the papers 3 times around this way. 3 times, everybody. Go to them. The 2 of you go to them, right? Pass to them. And yours will go to them as well. Guys, pass it now, Caitlin. Time's up. Time's up. Go to the side. 3 times. This is your 3. Pass them 3 times that way.
Can we check them?
So, who has rings here? Alright, now, number 1. So this, by the way, take out the GLQ things, and we're going to answer the GLQ at the same time, since we're pressed for time. Alright? Let's go. Take out the GLQ things. We're going to check, because some of the answers here double as the answers there. Alright, so let's do that at the same time. Okay, let's start from the bottom. Okay? Alright. I was serious, by the way, that I need the full name of the guy. Right? You just wrote his last name, you're not going to get it right. Okay. It was in the board the whole time, by the way. Newton's laws of motion. Like, seriously. Alright? But anyways, first law. We just talked about it before the quiz started, but I don't know if the video is still working or not. But it's working now, so we'll say it again. It was said anything like this: an object in motion, but what? Must stay in motion, the same motion, right? Unless a force acts on it, or an object at rest has to stay in rest. The way I actually like it, it would be like the object's velocity cannot change unless a force acts on it, or an object cannot accelerate unless a force acts on it. Or the way I really like it would be the object's momentum cannot change unless a force acts on it, right? That's the way Newton said it. It's a statement of basically energy states, that the energy of an object, the energy of motion of an object, cannot change unless the energy is applied to it, right? Unless you do work on an object, it must stay with the same energy level. So that's another idea that we talked about that. All right? Yes. That's the thing about things. If you just said an object at rest must stay at rest, is that right? Is that the whole law? No. In fact, you got to stay. An object at rest must stay at rest only if no force acts on it. But even then, it's the whole law. No, because it also includes an object in motion must stay in the same motion unless a force is acts. Which is why, to simplify, just remember an object's momentum cannot change unless a force acts on it. So to give the point, the person has to mention that it will stay at rest unless a force acts on it, and that will stay at the speed that it is, velocity that it is, unless a force acts on it. Don't forget, by the way, that you can stay at the speed and change direction, and that counts as a force act on it, right? Remember that acceleration does not change only the speed, it could also change the direction of the velocity. Right? It is only 1 point. 1 point for getting that first law correct. Right? Now the second law was, okay, we didn't do this yet, but I'll do it. Jennifer Tapia, what was the second law? Force equals, that's actually wrong. I'll accept F equals ma as the second law, but that's not the second law. It's actually A equals F over M. All right? That's actually the second law. All right? Now, let's accept that one, or we even accept it in words. Basically, the rate at which an object accelerates is directly proportional to the force that acts on it, and indirectly proportional to the mass. What does it mean? It means that the more force I put, the more it accelerates. But the more mass I have, the less it accelerates. Now remember we talked about free fall? And I talked about objects of different mass can fall the same rate. Right? So we can get a piece of chalk and maybe the lid of this thing right here. Right? Now, there are different masses, but they fall the same rate. And I said that when we did dynamics, we'll be able to explain why. And here's the explanation. All right? But before we talk about the explanation, let's talk about the number 3 on the quiz. Right? We'll skip the third law for a second. So we're going to number 3 on the quiz. By the way, that was the one check mark the person got it right. Right? What was the quote? And that's actually the number answer 2 for the GLQ. So pay attention. The GLQ says, give the dynamics definition of mass. So Raymond Rader, what is mass in terms of dynamics? Let's solve for it. No? Let's solve for it. Okay, so what does that mean? It is the ratio at which the force causes acceleration, but in other words, it is the quantity of inertia of an object. That's number 3. All right? That's what I asked, right? So mass was the answer. Because here's the thing. You must experience this in your life. It's very easy to push something light, right? But when something is heavy, it's hard to push it. You have the same force to give. But when the object is more massive, it's harder to do it, right? It's almost as if the more mass you have, the harder it is to apply a force to it. Is that with me? And that's what F=ma is all about. So when the planetary systems form, the gas giants are formed on the outside. Notice that? And then the rocky planets are on the inside. That's because when the sun ignited and the fusion started and solar winds started, all the mass of the cloud that had not yet fallen to the sun kind of blew out. Right? It's a moment of, as soon as fusion started, that happened. But on that push, heavier things, right, things which are more massive, accelerate less. Does that make sense? And so the rocky, denser stuff stays what? Near the inside, and the lighter gases got pushed to the outside. You see? It's a statement of this relationship. All right? One idea about why that happens. It's actually not exactly the right answer, but it's a simplification that is often used in astronomy class to explain why the inside of the inner planets are rocky and the outer planets are gassy. It's actually the oversimplification of what actually happened. But, you know, I don't like to teach the wrong thing. But it's a way that we often use in science to explain that. Now, quantity of inertia then is what mass is. All right? So, continuing number 2 there. What is force then? In terms of dynamics, force is what? Right. Or you can say it's also, but maybe answer the GLQ as we go on. It's also, you can say, it's the thing that makes the object what? Change? Change its acceleration, right? So it's the thing that makes the object accelerate. I think, another way of thinking about it, it's applied energy. Energy applied to the object to make it move. Are you with me? So let's keep going with number 2 there. What is inertia then? Susan, what would you say, what is inertia? Go back to the first law. What is that?
The way if it's at rest.
Yeah, so it's an object's tendency to what? To keep doing what it's doing. All right? To keep doing what it's doing. So next time, you know, you're trying to do homework, and your parents yell at you, it's like, you know, time to do homework. You're honest, so you don't have to worry about that. But sometimes your parents get in your case, right? And then your parents get in your case and to do what you need to do, and then you'll be like, listen, inertia. You know? I'm just tending to do what I do. And right now I'm not doing nothing. So unless a force applied to it, it's not going to happen. You shouldn't say that though, because then she'll force it. You know? Alright. You see that term? She'll force you? That's what that means. It's like you've got to be forced to change your pattern of motion. Right? And then acceleration. What is acceleration then? In terms of dynamics, we know in kinematics, acceleration is what? The rate at which an object changes its velocity, right? Which could be by changing the direction or by changing the speed. But in terms of dynamics, acceleration, all right, is a ratio of force to mass, right? Now, the thing I was talking about with the free fall, right? Now that we know the first and the second law, we can do this. So the acceleration of gravity, A for gravity, which is G, is the same for all objects. But see, the force of gravity, which is something we're going to talk about later in the year, is actually determined by this formula, right? Force of gravity is this formula, which we're going to talk about later in the year. All right? Now, as you can see there, these two objects are equally distant from the center of the Earth right now. So that's not a factor. They obey the same gravitational constant, so that's not a factor. The mass of the Earth is going to affect both of them. So their mass does matter for the force. It does matter. The one that has more mass will therefore have more force. Now notice that, let's talk about the third law. Pause that thought and let's talk about the third law. Third law. What does the third law say? Daniel.
For every action force, there's a reaction force.
There's always a reaction force. That's an acceptable way. For every action, there's an equal and opposite reaction. So go ahead and give the point if the person says something like that. Yeah, equal and opposite. There's always an opposite reaction force. Equal opposite reaction force. That is the answer. Now, let's name the laws. Number 2. The number 1 is law of what? The number 2 is law of acceleration. Very good. And number 3 will be action and reaction law. Okay, action and reaction. Number 2 is not the law of force. It's the law of acceleration. Yes. No, it's not the law of motion. They're all laws of motion. All right. No, it's individual points. Okay. 1 point per thing. Law of inertia, law of acceleration, action, reaction. Okay? Now, a reaction pair law, that's fine too. Alright, but the third law says that for every action equal opposite reaction. Let's talk about that for a second. And then we go back to our example of free fall. Every action is an equal and opposite reaction. So for example, my weight is acting on the floor, which means the floor must be acting on me. That's called a normal force. Alright? The earth is pulling on me, which means I'm pulling on the earth. Which is interesting. This force here is not us, the earth pulling us towards it. It's us and the earth pulling each other. Which means the moon being far away where it is and the earth being here, does the earth pull the moon? Is that accurate? Yes. Does the moon pull the earth? Is that accurate? Yes. Who pulls the other harder?
Oh, it's the same.
It's the same. The instinctive reaction to say, the earth pulls harder because the moon goes around it. First of all, that's not true. Actually, the moon does not go around the earth. Actually, we do not go around the sun.
What?
Okay? Actually, we go around each other. So look at the difference. Let's talk about the moon and the earth first, so that makes more sense. The actual center of rotation of the earth system is not, let's call it very center, is not actually at the center of the earth. It's actually slightly off-center to the center of the earth because the mass of the moon matters too, which means if you were watching, it wouldn't be this. It would be something more like this. Are you with me? Which means the moon, the earth does this little dance. And now, of course, the earth is also going around the sun, so if you're looking at it, the earth is going around, the sun is in the middle here, this moon, earth is also going around the sun. But as the earth goes around the sun, it does that little dance with the moon. Are you with me? So the earth, the orbit of the earth, what orbits the earth is not the center of the earth. It's that very center that orbits the sun. Are you with me? Except we don't orbit the sun. The sun and... Go ahead. You lost there? Let's do it. Let's do it again. I need a better model. All right? So you're going to be my son. Come here.
Oh, okay.
Okay. Okay. You're going to be my son. So people often think, forget the sun for now. People often think, go a little more like that because we're not on video. Okay. People often think that the earth, forget the sun exists, we're just looking at the earth system. People often think that the moon goes around the earth like this. Are you with me? That is not accurate. They pull each other. Because of that, the orbit is actually like that. So the Earth dances too because of the moon's pull. They pull each other. Are you with me? Which means, if you forget the moon exists, it actually looks like the Earth is doing that. Are you with me? A little circle. And so, if you actually look at what's orbiting the sun, it's the whole system that orbits the sun. Are you with me? The whole system orbits the sun. Right? But technically, we're not orbiting the sun because the same thing happens here. So because of the planets, the sun technically does what? The sun, no, I'm not talking about rotation. The sun actually... Right? The sun actually does a little cha-cha. I don't know what it is. But are you feeling the same? So go ahead and do your thing. So you see? That's what's happening. Now, it's not just... Thank you very much. Thanks. You are a great son. Alright? Now, that's the third law. Where every action and equal and opposite reaction. Are we clear? Yeah. So you guys graded number 1, number 2, number 3. Number 4 was the units of force. What is that unit? Sir Isaac Newton.
And they didn't put Sir.
You need Sir. You need Sir Isaac Newton. Huh? Facts. Number 4 is Sir Isaac Newton. Now, the ironic part is that number 5 is Newton again. Alright, it's Newton. Alright, now, the units of Newton, you just use this and do the dimensional analysis, right? So MA, F equals MA. Therefore, M is in what? Kilograms. And acceleration? Meters per second squared. That is the answer for number 6. Kilograms, meters per second squared. Alright? Now, make sure on your way out, not right now, on your way out, you're going to put the persons with the total. Okay, number 1 was worth 3. Number 2 was worth 3. Number 4 was worth 1. Number 6 was worth... No, 3 was worth 1. 4 was worth 1. 5 was worth 1. And then 6 is worth 1. So that means a total of... 3, 6, 10. Alright, so do this. 10s and 9s get 40 points. 10s and 9s get 40 points. Do it now. Okay? 8s and 7s get 35 points. 6 and 5s get 30 points. Alright? 4s and 3s get 20 points. Alright? 2s and 1s and 0s get nothing. 0. Okay? Now, hold on. Don't stop right now. Let's finish at least this question. Okay? Shh. Alright, so we stated 3 laws. We talked a little bit about it. The last thing I'm going to talk about is finish that idea that I was talking about with the free fall. Shh. Pay attention. So, why do they fall? Why do they fall? It's okay, I'll get it later. Why do they fall at the same rate? Listen up. Okay? Why do they fall at the same rate? Because it's true that this one, the heavier one, has more force with the Earth. So there's more pull between this and the Earth than there's between this and the Earth. So there's more force here. But this thing also has more inertia because it has more mass. Are you with me? So there's more force acting on this, less force acting on this. But this one has less inertia than this one does, and so the result is the same. One has more force, the other one has more inertia. Are you with me? And so the one that has more force also has more inertia. And because of that, they fall the same rate. Right? And then next class I'll talk about this a little bit more when we talk about weight and the normal force and stuff like that. We have much to continue here, but at least half of next class will be for activities. Look at the activities file and come up with ideas on what you want to do. Broadcasting, stop it.